So today what I want to do is just give you a couple of highlights. It's a 400-page book, so obviously I'm not going to be able to cover everything, but I just want to cover a couple of things I think are super important. And one has to do with the nature of emotion. So really for a very long time, depending on how you count, several millennia, the idea is that there were a set of emotion categories that were basically natural kinds, grounded in nature, each with their own kind of physical essence in the face, in the body, and in the brain. And in part of the book, in many papers, what I've done is just really bring the data to bear on this question, which I'm just going to summarize for you right now. Rather than flashing a gazillion studies at you, I'm just going to give you a couple of examples. How many of you have seen this girl before in anything? Great, perfect. So how does she look to you? Just make an inference, make a guess. About to cry. Usually when people look at her, they say, oh, she's sad, she's grieving, she looks like she's about to cry. This is my daughter, Sophia. People usually see her as looking sad or tired when they only look at part of her face, but when we bring in the whole context, it's really clear that she's experiencing a profound sense of pleasure. She's actually right here on her second chocolate drink at the Cologne Chocolate Museum. This little sweetheart is also experiencing a profound sense of pleasure. So the lesson here before our eyes, which is consistent really with hundreds and hundreds of experiments, is that people move their faces in many different ways during instances of the same emotion category. And what I'm showing you here about the face is also true when we measure the body, the physiology of the body. It's also true when we measure the brain. Doesn't matter whether we're measuring single neuron firing, whether we're using EEG, whether we're using MEG, whether we're using brain imaging. It's pretty much the same story. Now, when we look at this little fellow's eye region, we can see that he's making a movement that is associated with what many people believe to be the universal expression of anger. So, for example, when people look at this guy, does anyone know who this is, actually? No. Okay, so when people look at him, they think that he looks enraged, really furious. Actually, this is Jim Webb, who this is a photograph from 2006, who won the senatorial race in Virginia in 2006, returning the U.S. Senate to Democratic control with his victory. In the U.S., I like to use this example. I just like to have people take a minute and simulate what that would feel like. It kind of lifts up the crowd usually, unless you're in Texas or somewhere in the middle of the country. It goes over really big in Massachusetts, where I currently live. The reason why we see anger in this face when we don't have the context is because, in fact, this face symbolizes anger in our culture. And so the message here is that people not only move their faces in different ways during instances of the same emotion category, they also move their faces in exactly the same way during instances of different emotion categories. And again, the same is true when we look at other measures of emotion, that pretty much the bottom line is that variation is the norm when it comes to emotion. And I'm only now referring to categories that were presumed to be universal in their expression or in their bodily comportments. Actually, there's tremendous variability in what emotions mean across cultures, what a given emotion like sadness means. There's variability in emotion categories. Some exist in some cultures that don't exist in others. Certainly, we can make them on the fly using conceptual combination, but they don't exist as categories that are typically found in the discourse of that culture. And so the rest of the book really goes on to talk about the fact that emotions really aren't reactions to the world, as many people thought they were for a long time. Instead, really what they are your brain's understanding of what's going on inside your own body in relation to what is going on in the world, so that your brain can figure out what it needs to do next. So your brain doesn't encounter a situation, figure out what the situation means, and then react to it with an emotion. In a sense, you could think about emotions as being the embodied meaning of a situation, right? So emotions are actually what situations mean to your brain in a deeply embodied way. And what I'm going to do now is just kind of give you the 20,000 foot reason for why I have this hypothesis, and then I'll turn it over to our discussants for today. So in much of psychology, I would say for most of the history of psychology, since psychology became a science in the 1800s, what scientists did, it was basically take the categories of mental philosophy bequeathed basically from Western philosophy of mind, and went looking for the physical basis of those categories using the methods of the day, which were neurology, physiology. And that's pretty much continued to the present day. And in much of neuroscience, the same is true. People start with certain categories and then they go looking for the physical basis of those categories. In my work, and I think I'm in really good company here, we do something a little different. We actually start with the structure and function of the nervous system. And then we ask the question, well, how could a system that works like this, how does it produce the mental events and guide behavior in ways that we perceive in everyday life? And the answer that we came up with based on evidence from various domains looks something like this. That your brain, if you take your brain's perspective for a minute, really it has a reverse inference or an inverse inference problem that it has to solve. It's, for your entire life, it's trapped in a dark, silent box of your skull. And it is, it only learns what's going on around it in the world by scraps of information that it receives through the sensory channels of the body. So everything the brain knows about the world comes through the body. And it's basically receiving the effects, and it has to, like these changes in air pressure, changes in wavelengths of light and concentrations of chemicals are the effects of some causes, and it has to infer the cause based on only receiving the effects. And the same is true for the body. So your brain has to figure out what is going on inside your body only from receiving the sensory consequences of the changes in your body. So it has this reverse inference problem or inverse inference problem that it has to solve. And what makes the matter more complicated is that, any given change of light, any given change of, muscle tension or what have you, actually could have many different causes. So how does the brain solve this problem? How does the brain know whether an ache in your gut is hunger? The exact same ache in your gut could be anxiety. It could be longing for someone. It could be a feeling that someone is not trustworthy. How does your brain know which one it is? And the answer is it has to guess. And it guesses based on past experience that it has encoded as information is passing back and forth from neurons, as neurons pass information back and forth. But basically, what it has is memory. And you can think about your brain kind of doing the following thing. Your brain is basically remembering past experiences that are similar in some way to the present sensory array, meaning the array of sights and sounds and smells and internal sensations from your body. So it's asking the question, not what are these not what is this sensory information, but what is this like? What is this similar to? Now, in cognitive science, we define a category as a bunch of things which are similar to one another in some way. And a concept is a representation of those things. So in a sense, what you can say is that your brain is constructing ad hoc concepts as kind of anticipatory explanations or hypotheses or beliefs about the causes of upcoming sensory inputs and what to do about them and the motor consequences that are necessary. So the idea here is that it's reinstating past experiences in a generative way, but in a way that is similar to present sensory conditions as a way of making sense of those sensory conditions so that your brain can plan what to do next. And some of those patterns are, or those patterns always involve some interoceptive information, that is sensory information from your body. So to give you an intuition for this, I think this is an illustration of a couple of things that I think is really useful. One is that none of us, I'm assuming, have ever actually experienced an electrical pylon jumping up and down, right? But immediately we know what it is, because one thing that our brains can do is we can do conceptual combination. We can take bits and pieces of past experience and put them together in new ways. Neuroscientists call this generativity. Cognitive scientists call it conceptual combination. Another thing that this illustrates is the concepts that our brain is making are embodied. I don't know about you, but, well, how many of you can hear this pylon jumping? Yeah, I can too. How many of you can feel your chest thumping? Yeah, I can too. Actually, I've seen this dozens of times and it never loses its effect. So the really interesting, cool thing about this is it illustrates this amazing power that your brain has to modify the firing of its own neurons. That is the reason why, if you can hear this thumping, or you can feel the thumping in your chest, it's because your brain is able to modify the firing of sensory neurons in the absence of direct sensory input. And of course, we have lots of fancy names for this. We sometimes call it simulation. We sometimes call it embodied cognition. We can call it perceptual inference. I just called it making ad hoc concepts. How you know something is important in science is when the same phenomenon has been rediscovered again and again and again and given lots of different names, like this. And my suggestion to you is that the reason why these kinds of images and so on are really compelling is because they represent special examples that unmask for us what our brains are doing really all the time. If you weren't able to make a concept for this, you would be experientially blind to what it means. You wouldn't experience the thuds, you wouldn't experience the sounds. It really would be kind of visual noise to you. And the reason why it's embodied, these concepts are embodied, is because your brain actually evolved to control your body. So your brain didn't evolve for you to think or to hear or even to feel. That's not why brains evolved. Brains evolved to control bodies. As bodies got bigger and more complex, as niches got bigger and more complex, brains got bigger and more complex. And it's your brain's business, basically, to be budgeting your internal resources all the time, whether you're aware of it or not, whether you're conscious of the sensations or not. Your brain is budgeting internal resources all the time, like water, salt, glucose, and so on, to keep you alive and well. It's basically running kind of a general energy budget. And we call this general regulation allostasis, which is the predictive regulation of the body, that the brain's job basically is to anticipate the needs of the body and attempt to meet those needs before they arise because it's metabolically efficient to do so. Because your brain is your most expensive organ, it takes up about 20% of your metabolic budget, and the intrinsic activity of the brain, much of which is devoted to regulating the body, takes up about 70% of that 20%. So basically about 14% of your entire metabolic budget is devoted to regulating your body. So it's an expensive endeavor and it has to be done really efficiently. And so evolution has given us a bunch of ways that this can occur. And one of them is that this regulation is occurring predictively, right? So the idea is, and I still would call it an idea, but it's an idea with gaining a tremendous amount of support, is that when your brain is making these ad hoc concepts and it's trying to regulate action and regulate the internal systems of the body in service of that action. In the service of those actions, it's doing it predictively in the following way. That your brain is basically starting with initial conditions, right? So from your brain's perspective, the initial conditions are of your body in the world, right? In the niche, in your niche as it currently stands. And it's projecting itself forward in time, predicting what the body has to do next. That is what the motor actions the body has to take, and the viscera motor changes, the viscera meaning viscera, changes in the viscera in the internal bodily systems that support those motor actions. And the idea is that these commands that preparing the body to act are basically also sending predicted sensory consequences of those actions as simulations, as you, something like very similar to what you experience in looking at the jumping pylon. And these predictions actually change the firing of your own sensory neurons that begin to create your sensations and experiences on the basis of these anticipated sensory inputs. And these predictions are not just anticipating sensory inputs, they're also, you could describe them as ad hoc concepts that are sort of attempts to causally explain these anticipated sensory inputs. And so your brain is basically running a sequence of complex, dialogues with itself. It's mainly talking to itself, basically, in preparation for telling the body what to do. And embedded in those commands are the proposed causes of sensory inputs. And then constantly information is arriving from the world and from the body, which can either confirm those predictions, in which case action just is the prepared action just occurs, unfolds, and therefore these sensory inputs can be said to be categorized. Or if they don't match, then your brain can take in the errors of prediction and modify its action plan. And we have a really fancy name for that in psychology. We call it learning. So the brain can learn new information so that it can predict better the next time. And this is how changes in air pressure become sounds, how changes in wavelengths of light become vision, how chemicals in the world become smells, and so on. And it's also how interoceptive sensations from your body become simple feelings of affect, feeling pleasant or unpleasant, feeling really worked up or really calm. It's also how your brain builds emotions. That's basically the hypothesis. This is how an ache in your stomach can become hunger or anxiety or longing or distrust. Now, there's a lot more that the book talks about, but these are sort of the basic ideas that are summarized in that book. And then we talk about really the consequences of that for interpersonal relationships, for raising children, for health, both physical and mental health, really breaking down the boundaries between mental and physical, between mind and body, and really more generally for discussions about what it means to be human.